Yo guys, so you're probably wondering what the hell is this thing? And I know this isn't pretty, but think of them like a ghetto knockoff version of the upcoming Apple smart glasses. So I ended up building smart glasses, which allowed me to measure the height and length of any object using a technology called Lidar in combination with data that I get from an inertial measurement unit. So the whole point of this project was that I wanted a hands-on experience using the technology known as Lidar. Lidar stands for light distancing and ranging, and pretty much it allows us to measure the distance of an object simply by using invisible light. With Lidar, it sends out a pulsed laser light and then it reflects it back to the sensor. And since we know the speed of light as a constant, we can measure the distance of an object, seeing how long it takes for that light to come back. Now, if you rotate that on multiple axes, you now have dots that are all around you in a sphere, essentially. And then you get what's known as spherical points. So using a distance and a tilt angle and a pan angle, we can get spherical points all around us. Then using some math, we can convert those spherical points into Cartesian points, and now we have what's known as a 3D point cloud. This is all actually really cool, and you can find lots of examples on YouTube of people doing this. It has serious implications for autonomous vehicles. See, autonomous vehicles need to know how close or far obstacles are away from them. Now, for this project, I wanted to kind of simplify it down, and I wanted to use something that could be a wearable. So that functionality that I wanted was to be able to measure the height and or the length of objects using Lidar. Now, using basic trig, we know that if we have the distance to an object and the angle of elevation, we can measure the height of that object. So that's one easy way of doing this. Now, to get that angle, we can use an IMU sensor, right? So an IMU, also known as inertial measurement unit, is kind of what you will find in your phone. That cool thing that tells you your orientation of your phone and helps you track where it's at. Now, the reason why I'm using an IMU is getting your absolute orientation is actually a very complex process. It involves a gyro, magnetometer, accelerometer, and sometimes there's even a fourth sensor to get your absolute orientation. But inertial measurement units are pretty much units that have all these sensors combined on one chip. And they do the whole math for you and output simple Euler angles. So that's actually very convenient, and I'm gonna use that to get our pan and tilt angle. Then with the Lidar sensor, I can get the distance, and from there, I convert those spherical points into Cartesian points, and I can then find the distance between those 2 points, or I can use our trig method and just use the angle height of an object. So either way, I kind of want to give this a try. I think this is a cool project. So let's take a look at what we'll need to build this and the code we'll need to do this. So for the parts for this project, you're first going to need a Lidar sensor. So I'm using the Garmin V3HP. It is a true Lidar sensor. It's a standard I2C device, so you can connect it to your Raspberry Pi or Arduino, and it actually works quite well. Now, this device is definitely pricey, and if you want to kind of do this and you don't want to spend all that money, because trust me, I was cringing buying this thing, you can use one of the cheaper time-of-flight sensors. They aren't true Lidar, but they still get the job done. And you can even use a sonar sensor, honestly. It'll still kind of do the same thing. Now, you're also going to need a 680 microfarad capacitor, and that's for decoupling with this Lidar. Don't try to skip on that because you're going to run into stability issues. Next, I have the Adafruit IMU. Like I mentioned before, we are going to need an IMU to get those Euler angles and just to make life easier. And you know, I think it's just a lot easier than trying to buy all the components separately and trying to do it all yourself. Now, I'm also going to use this cheap LCD panel that I bought off Amazon. I think it was like $5, and it's just so I can output the data to somewhere so I can physically see it as I'm holding the glasses. So, you know, if you want to use this, this is also a great option. Now, for this project, I am not at all thinking about power consumption. So I'm going to power this in the most inefficient way possible by using a 9-volt battery and sending it through a 5-volt voltage regulator. And this is what you're looking at, the 5-volt voltage regulator. Again, it's not super efficient, but we're not really worried about that for this project, so we're just going to use this. Now to power this all, the brains of this project will be an 18 mega 328P, also known as a chip that you can find in the Arduino Uno. I'm using this simply because I have a lot of these lying around, and honestly, this has enough horsepower that we need to run this whole entire project. Now I'm also going to use a push button just to start and stop the measurement. And I'm going to grab a couple of resistors at 4700 kilo ohms, and that's just so I can have a pull-up resistor with the Garmin Lidar. And I almost forgot, we're also going to need a laser because lasers are cool and they make projects just super awesome. But no, realistically, we need a laser because you're not going to see the light that gets emitted from the LiDAR sensor, so you're not really going to know where you're pointing the LiDAR sensor at exactly. So a laser at least helps focus that by giving you a pointer to look at and to know where you're facing. Now, I'll provide a link to all of these items in the description below. Just know that these will be Amazon affiliate links, so if you make a purchase, I might get a commission from that. But, you know, doing that will definitely help the channel and helps me be able to afford doing more of these cool and interesting projects. So let's take a look at the code and see what we need to code this. Alright, let's jump into the code of this project. So for this, I'm writing this in Arduino code, which is pretty much C++. So if you're familiar with Arduino, this should kind of be natural and it shouldn't be too hard to follow. Now, I'm not going to go through all this code because it's quite a lot and a little bit tedious. I just want to point out some of the main things just to get an idea. This will be posted on GitHub and I'll add more comments before I post it, just so it's a little more clear. So the main thing is in the setup process, what we're doing is we are looking for the IMU. So IMU, we're making sure that it is attached before we begin. If not, we print it out and tell the user, oh no, something's wrong. We're also enabling fast I2C, and we're going to need this for the LiDAR light because LiDAR light refreshes at around like 500 kilohertz per second. So we're definitely going to want to enable that just so we can make use and get those fast readings. And finally, we just enable a button as a interrupt button. So in our interrupt service routine, when we press it, we pretty much create a flag that we'll check within our loop. Now we have a couple of functions down here, just helper functions like getting a distance, calculating a point distance, converting into inches because I'm in the US, so we're going to use just inches, degree to radians, and you know, all this just kind of helper functions that will probably be self-explanatory. This one function I think is interesting. I should kind of talk about this. This is sanitized data. So with this function, essentially, I found that when you're using the IMU, it's very sensitive. So ideally, I want to measure things in a straight line. So if I'm measuring the door, I want to measure from the bottom to top. And ideally, I'll just look at the door and move my head from the bottom, move it upward. So in theory, the X direction should stay the same, and our Y direction should be the only thing that's changing. In reality, there is some some movement in your pan or X direction, and which, is going to throw off the measurement and throw off the distance a little bit. So to counteract that, I kind of just compared which one was bigger. Was your Y bigger? Was your horizontal bigger? Or was your vertical change in direction or angle bigger? And whatever one's bigger, the opposite one I changed to all zeros, and I found that this to work. So that's just like really the only kind of gotcha function here. The rest of this is pretty clear. Clearing array, printing array. In our loop, what we're doing is we're first checking the calibration status. So with Git system calibration, the IMU that we're using, what's really cool is that it is self-calibrating. Now, the one thing is before you get a reading, you want to make sure that the calibration status is pretty much all three. So it returns different values, but you want to look at the system value and make sure it's a 3, and that means everything's calibrated. And that status is not permanent. It's going to change as you move around. So if you start moving around real quickly, that 3 might become a 0 or a 1. So what we want to do in a loop is first make sure that the calibration status is a 3. Then when we get the distance, what we want to do is make sure the distance is just not 0, because that's not going to help us. So if that is the case, we're going to print all this stuff out and just kind of complain and say we can't really do anything, it's not ready. Otherwise, we're going to check that flag that I mentioned in the interrupt service routine to see when it was pressed, to see if the button was pressed. And there's 2 presses. The first press is what we want to kind of tag as our first points on a line. The second press we want to tag as the second point on a line. And then each time what we want to do is the first press, we pretty much get a bunch of points at that current moment in time. We calculate the average of those spherical points, and then the second press we do the same thing. We get a bunch of points and we calculate the average of those spherical points. Then we do that sanitized data function I was telling you about, and then we have two spherical arrays. We convert them both to Cartesian arrays, and finally we find the distance between the 2 points and we print out the distance. So we're almost at the end. So the next step was for me to flash this to the 18 mega 328, and then I did my least favorite part of this project, which is soldering. Solder everything together and try to mount everything, and here's what we end up with. Okay, so here's how these are working. So what's happening is I have this button right here. So we have the 9-volt battery connected to the voltage regulator right there with a button. The Lidar and the laser are up front. You kind of see the line from the laser. And then we have the LCD right there. I'm gonna hit the button for start measuring. Then it's going to change to stop measure. And that just tells me that I'm ready to stop measuring. So I'm gonna hit stop measuring. And there you go, I have distance of less than an inch, which is good. That tells me this is working because I didn't remove this at all. And you know, in the perfect world, that would be 0. But considering there are some variations, stuff like that, less than an inch is still good to say we didn't move this. So one more time, just as a quick test, we hit that. And it's going to say stop measuring. So let's go and hit stop measuring. And again, we have 0.29, and that's the result in inches. And that tells us that we did not move this at all. So as far as how all this works, it's actually not too bad. So I measured a couple of things around my apartment, like I measured the height of my bookshelf, and I got 32 inches, 32.62, and the actual height of the bookshelf is 30 inches. I also measured this keyboard that I have, and I got a length of 54 inches, where the actual length is about 52 inches. Now, so we can see it's not actually that bad. It's a little bit off, but that's to be expected because if you look at the data sheet, when you're really up close to things or less than 2 meters, you're going to have a measurement, distance measurement that's going to be off by about 2 inches. Now, that doesn't mean this was perfect. For example, I measured the height of my door and I got 70 inches when the actual height is 78 inches. And there were some things I measured that it was just completely off. But for a lot of things, it was pretty accurate and kind of close to where it would be, plus or minus 2 inches. So, like I mentioned at the beginning, the purpose of this project was to learn about Lidar and to get hands-on experience of using Lidar. And this project allowed me to successfully do that by using the Garmin Lidar and to use it to measure the height and distance of objects in combination with an IMU. Now from this, I definitely learned a lot myself from doing this whole project, and I also learned that I really hate soldering. It's the part of the project I hate, and I also learned that I could have took more time in the actual physical design of the glasses. I was more excited about the code and about the theory than about the physical product. So I think in the future projects, I definitely want to take more time and try to polish out that final product just so they look better and not just mess that I have right now. But overall, I'm satisfied with how these turned out. I think it was a great learning experience, and I highly suggest that you try it out if this interests you. So guys, if you like this video, give it a thumbs up. Tell me what you think in the comments down below. If you want to see more videos like this that I post in the future, go hit that subscribe button. And as always, thank you for watching and stay tuned for another galvanizing video. Thanks.